During the last decade or two, increased awareness of the health risks caused by contaminants in our drinking water has captured widespread media attention.
The levels of contaminants often change, and they're usually in response to either new scientific discoveries or public pressure, such as the Aaron Brockovich movie, where the public is made aware that there is a health risk. Then those are reviewed by committees.
As a result, substantial revisions have been made to the regulations that control the types and concentrations of contaminants allowed in our water supplies. Hi, I'm Dave Bender. Primary drinking water regulations periodically change, and owners and operators of water systems can find it a challenge to stay in compliance with these changes.
The issues facing this well are that arsenic levels are about 20 parts per billion, and the new standard is going to be a 10 part per billion standard. Old was 50 parts.
The maximum contamination level, MCL, for substances in drinking water that are harmful to human health is limited by the United States National Primary Drinking Water Regulations. These standards are set by the U.S. Environmental Protection Agency and implemented by the State Department of Health Services. Any water system previously in compliance with drinking water standards can fall out of compliance for two main reasons. First, when a source of contamination impacts the water quality of the water supply.
This well was put into service in the mid-60s, directly into our distribution system, approximately 1,000 gallons a minute. About 1997, we got a detection of PCE in our system. As we approached the maximum contaminant level, we decided we're going to have to do some sort of treatment or abandon the well.
And second, problems of non-compliance can arise when regulations are changed to become more stringent.
Well, for small systems, it can really be a shock when the regulations change, where you've been in compliance for maybe 100 years and all of a sudden the regulations change and you're no longer in compliance.
Staying in compliance with standards is not always easy. The process can be very complicated, time-consuming, and sometimes costly. There are a number of solutions and difficult decisions to make.
Is it cost-effective to re-drill a new well? Is it cost-effective to put in a treatment plant or point-of-use type of treatment, or go elsewhere and find some surface water and use that for supply?
What appears to be the best buy up front may not necessarily be the best long-term solution. In time, the easiest, cheapest solution could cost the most and end up bankrupting your company over time.
Nobody wants to make the wrong decisions, so knowing what to do and when to do it can go a long way in helping to avoid major problems down the road. In the following program, we're going to look at the decision-making process for maintaining and obtaining compliance. We'll use a decision tree to guide us through the process from identifying the problem to the final solution. You've already heard from a few of our guests: DHS Staff Scientist Steve Mint, Consulting Engineer Alex Peterson, Water Production Supervisor Fred Stafford, and General Manager Teresa Tanaka. They will be joined by DHS Sanitary Engineer Richard Haberman, Senior Scientist Maria Takanen, Senior Project Engineer Brian Zinn, and Water Quality Technician Gary Young. Together we will discuss a variety of approaches to compliance with standards. So let's go to the beginning of the process and look at the first step, that is, to identify the problem. Causes of contamination can be both natural and man-made. Naturally formed chemicals such as arsenic can leach into the groundwater. Agricultural fertilizers such as nitrate can seep through to aquifers used as drinking water sources. Accidental toxic spills and hazardous waste such as petroleum and PCEs can cause long-term problems.
Most often the causes of contamination are naturally occurring, either some sort of chemical in the soil that's there naturally, or perhaps like on a river like this, it may be a spill upstream of some chemical or petroleum or even an automobile accident might impact this facility.
Examples of the most common contaminants include arsenic, nitrate, perchlorate, perchloroethylene, uranium, chromium, petroleum, lead, and mercury. Routine monitoring will disclose whether or not contaminants are present and at what level. But as soon as you become aware of any changes in contaminant levels or of standards that might affect you, action should be taken immediately.
Every month, take a sample from the same site to see how that water changes. Once you've got that in place, you at least know what the high end and the low end, and you're always going to be worried about the high end of your arsenic concentration is and what you have to treat.
Changes in the regulations may affect not only compliance issues, but also how the sample is taken.
Whereas in the past, you could view your water quality out in the distribution system. So this well, if you moved out and down the street, it might have mixed with other waters and could be more a lower arsenic level, but now it's really entry point, so you have to measure it right here, and you get no benefit for any blending in the distribution system.
Keeping up to date on changes in drinking water standards is crucial to staying in compliance. There are many ways to get the information.
DHS will send out emails, but AWWA, which is the American Water Works Association, will send out a news flash informing you that EPA or DHS is going to change one of your mandates, is lower it, like maybe nitrates or arsenic, the levels. And so you'll get mandates that say, warning, this is coming up, and they want your feedback, so you can send a letter. So there's different ways that we can get our information.
What I would suggest for small systems is that they become more active in the water community and be aware of when these regulations are proposed. Generally, they're proposed 3 years before they go into effect. The department maintains those on their websites, but also water agencies will generally have a handle on what new regulations are coming down the road.
Once you identify a problem, you need to move on to the next step of the process. That is to consult with DHS. When a water utility realizes that they have a contaminant that needs to be addressed to meet new standards, the first thing they should do is contact the Department of Health Services Division of Drinking Water District Office. They will give you advice and guidance on what they think is the best approach.
As soon as the regulation has been adopted and is final and there's an effective date, it's advisable for all small systems that are going to have to make a change to contact our office about the change that they anticipate they're going to have to make.
It's a good idea to be talking to your DHS representative to understand what they're looking for in the water quality records. They certainly have seen many different water systems and are going to have the benefit of that breadth of knowledge. They can talk to you about what's important to look at and maybe give you some shortcuts or give you some focus so that you're spending the money effectively.
What money, you might ask? Where do you find the capital to even get started with solving the problem? After all, you may need to hire consultants and engineers, and it all costs money.
If you're a small system, you may have a problem where you can't afford to go out and hire a consultant or an engineer right up front. The program that I work for is paid for by federal funds, and we will actually provide you assistance, someone that will actually come to your water system and help identify all the problems and solutions and help you work through the massive amounts of paperwork to get grants, to get funds, and to identify all the solutions that you have.
So don't try to go it alone. The sooner you contact DHS, the better. Now, many of you will have a lot of approaches available to you, and in some cases, very few. Whatever your situation, it is really important to carry out a thorough investigation of your options. Let's move to the next step of the process. That is to explore approaches. As you move into this phase of the process, you will probably need to hire consultants and engineers. A high degree of scientific and technical knowledge is often required for the research and development of alternative solutions.
But you need to remember that you're in charge. You need to make sure that the engineer looks at options which are appropriate for your water system, that the solutions are workable or manageable through your water system. You need to ask them questions like, do I need to bring on additional staff? Do I need to be worried about costs of waste if wastes are involved? Or just other questions that may come up as you're discussing the possible solutions with your local staff, whether it's DHS or your LPA. All these things, remember that the consultant is working for you and you need to be involved helping give direction so that you do not end up with a solution that your water system can't afford or a treatment plant that no one in your organization can operate.
There are 3 main approaches you can explore when dealing with maintaining and obtaining compliance. You can merge with a nearby water system, find a new source of water, or you can consider treatment for removal of contaminants. Too often, system owners, when faced with news of noncompliance with primary drinking water standards, jump right to the treatment option. This decision may saddle the system not only with capital costs, but also with ongoing, higher than expected operations and maintenance costs. By looking first to alternatives, the system owners may avoid those costs and provide higher quality water.
Bottom line in meeting any regulation is costs. How cost effectively can you deliver safe, reliable, in appropriate quantity water to your customers?
Well, once you're looking at all the options, the most critical thing is to look at the final cost. And you need to look at all of the costs of whatever your solution is.
In some cases, we've had utilities connect to larger utilities and go out of the business of being a water supply system. We've had utilities destroy their contaminated well and replace it with a new well. We've had utilities construct new wells and blend the two wells so that the effluent from the blend meets the standards. And we've had utilities build treatment plants such as this one to remove the contaminant.
The Department of Health Services will be able to give you useful information regarding your available options.
Once you've contacted them, you can use the information that they have to identify if a new source is possible in your area, possibly abandoning the old source if it's a well and drilling a new well, perhaps looking for an uncontaminated aquifer. Or it may be that they have information that that entire area has this contamination. They may want to change you to surface water out here. Or they may have information that there's another water system next to you that has perfectly fine water, and they may point you towards consolidation to solve your problem.
This well in the county of Sacramento will soon be out of compliance for levels of arsenic. Their answer is to construct a new well at a second location.
And it looks like if we move a couple of miles to the east, we should be able to find a water supply that meets the arsenic rules. It's going to have manganese and iron, which are very treatable, so you're still having to treat and there's still costs associated with it. Just not the issues and difficulties associated with arsenic.
It may not be possible to merge with another system or find another source. The Linden County Water District has about 540 connections and is too far away from any other system to merge. They must explore other approaches for staying in compliance.
Do we have to abandon the well? Is it in our other wells? So does it involve the whole aquifer? And if we've abandoned the well, we use the rest of the wells and determine whether we have to re-drill one, build a new well, or options are we cannot, in our district, because we're so far away, there's no way of getting water from any other source. But there is a chance, there's surface water available in the future for the district to possibly use.
Treatment may be the only remaining option to solving the problem. However, whenever you move into the area of exploring treatment, there are a lot of very important considerations to make. The treatment option needs special attention. Let's take a closer look.
The last option that we want to look at once we've identified a contaminant is treatment. Treatment needs to be adequate, appropriate, and cost-effective. It has to be adequate for the size of the water system. It needs to be an appropriate technology that the system can operate virtually for the life of the water system. And then it has to be cost-effective. If the water is too expensive to treat, you can't afford to produce it.
We can't stress enough about the planning for long-term costs when considering the building of a treatment plant. But we'll talk more about that in a minute. First, we want to give you an idea of what a treatment plant looks like. What components are necessary? How difficult are they to operate? How big are they? Of course, treatment plants differ from one utility to another, depending on the type and level of contaminant and the amount of water pumped through. However, to give you a general idea, we're going to visit a couple of typical treatment facilities. This East Valley Water District facility in San Bernardino, California, had water supply sources that were exceeding the nitrate MCL. They applied to DHS for a permit to construct a treatment plant for the removal of nitrate and are now in full production. Let's join Brian Zinn, Senior Project Engineer for Basin Water.
What we manufacture are ion exchange units. This container here is a 10-foot by 30-foot container. It's a 1,000 GPM containerized treatment unit. It's completely fabricated in our shop, and it's prefab. We put it on the site and it's ready to go. What we do is the raw water comes in through this header. The first thing it hits are the pre-filters here. These are 5-micron bag filters. They're used to remove particulate matter, sand, dirt, anything like that out of the well water. The reason being is we want to protect the ion exchange resin from being fouled by this material. Once the water goes through the bag filters here, it goes out this header, and then it goes into the treatment unit, which we can go look inside of here. And I can show you the vessels. Okay, this is the inside of the treatment unit here. Inside of the treatment unit are these large fiberglass vessels which hold ion exchange resin. The ion exchange resin is capable of removing nitrates, arsenic, perchlorate, uranium, chromium-6, vanadium, and several other contaminants. At this particular site, it's being used to remove nitrates. What happens is the raw water from the well comes into the unit through the bag filters, which we already saw. That removes any particulate matter. The raw water, which is high in nitrates, then enters the top of the vessels, which are in service, flows through the resin. The resin removes the nitrates, and then the treated water, which is now low in nitrates, exits the bottom of the vessel and enters the distribution system. The vessels are all controlled by a computer system, which is located at the other end of the treatment unit, which we can go look at here. The ion exchange process is actually quite simple. We're simply attaching nitrate ions at this site onto the ion exchange resin. Once the resin has reached its capacity, the resin needs to be regenerated, which we do with a sodium chloride solution, a brine solution. The brine solution is pumped across the resin. Once that's done, we then need to rinse the vessel before we put it back into service. All the motor-operated valves, miscellaneous piping, and eventually the computer are used to control the regeneration, rinsing, and sequencing of the vessels. The computer here provides a display of everything that's going on to the operator. We can enter set points to adjust the unit for nitrate, arsenic, whatever application it is. We have alarm set points. We also have trending. It's a fully functional HMI package. The unit's designed to be unmanned. If there's any alarms, the unit will dial out to the operator. As part of the regeneration process, as we described inside the unit, the vessels are full of ion exchange resin, where nitrate is attached to the resin beads. Once the resin has reached its capacity, the resin needs to be regenerated. When we regenerate it, the resin stays in the vessel, and we pump a salt solution, sodium chloride solution, across the resin. And as that happens, the chlorides reattach themselves to the beads, the ion exchange resin beads, and the nitrate leaves the beads in a liquid stream. The liquid stream is then stored as a waste tank. Now, to make this regeneration process work, we have a salt storage tank here. This stores a saturated brine solution. This is full of basically table salt. We keep liquid at the bottom. That's our salt solution. When necessary, the treatment unit will take a vessel out of service for regeneration. It basically turns that vessel off. We take the salt solution out of this tank, pump it through the vessel across the resin. That removes the nitrates. That stream then comes out of the treatment unit and is stored in these two large waste tanks over here. The waste disposal is taken care of by a truck. There's large white PVC pipes on the bottom of the waste tanks, which are then piped to a locked box out on the street. A waste hauler, which is a large truck, can handle about 5,500 gallons, drives up, connects to a Camlock connection, and basically sucks the tanks empty and takes the waste away to a disposal site.
Just a few miles away, also in the East Valley Water District, is a well that was in service for 30 years before perchloroethylene, or PCE, was detected in the system. Rather than abandoning the well, they opted for treatment. Fred Stafford is the water production supervisor.
We decided after extensive study to put in the liquid phase granular activated carbon cells that you see in the background. The effluent of the well pumps directly into that singular tank to the left of the 4 cells here, where we drop out the heavier particles and then pumps directly into this top pipe here, which goes over into our manifolding system and directly to the 4 cells for the treatment process. The water comes into the top of these cells where it goes through this granular activated carbon. This is an example of what's in there. As the water flows through this carbon, the PCE, the contaminant here, attaches to this carbon and begins to saturate that. You'll notice in the background we have different stages where we sample for PCE at different stages of the carbon to see where the breakthrough might be. Before we get a detect at the effluent of that cell, we're going to remove the saturated carbon from this cell and replace it with freshly regenerated or virgin carbon. When we pull the carbon out of this cell, it comes out through this apparatus right here, is pulled through a vacuum into a tanker truck. He then attaches a hose from his fresh compartment and fills the chamber again with 20,000 pounds of reactivated carbon, and we're ready to go again. Fortunately, we're able to take one unit offline at a time without taking the plant off of line. We can continue to pump at full capacity while we're doing the reactivation of one of our cells.
Now that we have a better idea of what a treatment facility might look like, let's pick up with Steve again and talk about costs.
If you choose treatment, you need to look at the cost of the operator, the cost of the chemicals, the cost of the power, and the cost of waste. I'll give you an example. If I spend $1 million on putting in a new source, then over 20 years that will cost each customer about $25 a month. If I choose a treatment option where I have to pay an operator $65,000 a year, the customers are going to be paying $50 per month per customer. So this is a long-term cost. Clearly, if we spend $1 million up front and get a new source, the savings to the water system is tremendous in its monthly bill because we have that built in, the much lower cost. We're able to pay it off over time. So you really need to look at those cost options.
In the long term, you may find the operation and maintenance cost for running a treatment facility will be greater than your capital cost for building the plant.
What drives those O&M costs are that you're going to have media disposal, you're going to have additional energy costs, you may be discharging to the sewer who's going to charge you capacity charges, a lot of related tangential issues that are going to come back and get you.
You know, so, personnel to run this treatment site. Are these people of the appropriate grade as far as a treatment operator goes? That can change.
That's very true. Whereas you may have had, just as at this well, you've got chlorination, you're going to pump, you're going to disinfect, and out it goes to the system. Now you may have pH adjustment, chlorination, readjustment of the pH, as well as having to deal with the media, making sure everything's operating properly, and all of the water quality analysis to demonstrate that your system's working. You're right, there's a lot of additional manpower that's going to go to each of these sites.
We visit all of our sites at least once a day. This particular plant we usually visit several times a day. Again, we're trying to get more familiar with it. As we get more familiar with it, we'll probably spend less time here, but being as it is a treatment facility, we do spend a little bit more time here.
When we added the carbon activation units, again, we're coming out here once a day, but at this point in time, there are quite a few more items that we have to check. There's more readings that we have to take, differential pressures, more maintenance items, security issues that we have to check out here. Not to mention that about once a year, we have to reactivate the carbon in each one of the cells.
Most water treatment plants have your initial capital costs, but water utilities are today realizing that it's the operational expenses, the monitoring expenses associated with a treatment plant, and finally the disposal of the waste residuals generated by the treatment plant that generally are their largest cost concerns, and they determine whether or not a lot of treatment plants are built.
Another important issue to consider when looking at treatment alternatives is whether or not the treatment plant will fit at the site. Is it compatible with what's around it? Do you have the utilities available?
This well site is pretty typical of a lot of well sites. They may even be larger than many. What you find, though, is there's not a lot of room here available for adding treatment, for being able to maintain this facility after you construct it. For example, if you were to put an arsenic treatment plant here, you would have 26-foot tall, 12-foot diameter tanks at this site. And you can picture that that's not going to sit very well with the people that live next door.
Once we decided to go with this type of treatment process, one of the considerations that we had to make was, do we have enough room at this site to do what processes we need to do? One of the considerations was, do we have the room to bring a truck in here to pull the spent carbon out of these cells and at the same time bring enough load, a big enough load to place new carbon or regenerated carbon back into the cell? Fortunately, we did.
As you explore approaches, you may find that you have no alternative but to go with some sort of treatment. On the other hand, the capital cost of building the plant could be prohibitive. One solution is to lease.
We manufacture the treatment units in our factory, and we actually lease them to the owner. There's no capital outlay on the part of the owner to get the project going. We install the unit, get it running, permit it, and once it's running, we then have a contract with the owner to bill based on acre feet treated.
These units can be designed to provide solutions for systems of different sizes and requirements.
The unit behind us is capable of 1,000 gallons per minute, but we can change the flow rates that the unit will treat by reducing the number of vessels or changing the size of the vessels. We have other treatment units which can go down to as low as 50 to 100 gallons a minute.
It's also important to know that the quality of the water you have at the source may affect the type of treatment you're considering, especially if other forms of treatment are already in use.
You know historically what some of that water quality is, but it may not be sufficient to define all that you need to know to pick the appropriate treatment option. A number of constituents in water can minimize the effectivity of various treatments, such as silica, such as phosphates, such as your pH, or even something as minimal as your total organic carbons.
Any utility that is proposing changes to their water system should get the community involved. Costs are usually of great concern.
We only have 542 connections. That means customers. And so we'd have to really look at the capital costs and the overall maintenance and operations of whatever we decide to do, whether it be treatment, whether it means to join a surface water source. We'd have to look at that and find out if it's equitable for the community, because the costs actually go back to the customers. They're going to have to raise rates. We'll have to have public hearings, public meetings, and this is their system.
If the people who are drinking the water feel they have a voice in the cost of the water, the treatment, and what the water system is going to ultimately look like, they are more likely to go along with it and not raise objections.
Hopefully, any solution you come up with will have the backing of your community, but ultimately, DHS has to approve any interconnection with another system, any new source, any blending of existing sources, or the addition of treatment. Any change you make to address compliance with standards will have to get permit approval from the Department of Health Services. Well, that just about completes our discussion on the decision-making process for staying in compliance with primary drinking water standards. Before we go, though, let's do a quick recap. As the maximum contamination levels allowed in drinking water by the EPA are reduced, more and more utilities face problems of non-compliance. For example, as the level for arsenic dropped from 50 parts per billion to 10 parts per billion, the several hundred systems in violation turned into thousands. Systems can fall out of compliance when regulations are changed and/or contamination impacts a water source. To guide you through the process for maintaining and obtaining compliance, we suggest you use this decision tree. The first step is to identify the problem, then consult with DHS. The next step is to explore approaches, which includes ways to merge systems, finding a new source, and considering treatment. Causes of contamination can be natural, for example, naturally formed chemicals in the soil, or man-made, such as accidental toxic spills. Examples of the most common contaminants include arsenic, nitrate, perchlorate, perchloroethylene, uranium, chromium, petroleum, lead, and mercury. Adhere to your schedule for monitoring and increase the frequency if you are suspicious of changes in levels of contaminants. Make sure that water quality measurements for contaminants are taken at the point of entry into the system and not some distance away. Keep up to date on primary drinking water standards. Be active in the water community. Visit the DHS website on a regular basis. Consider joining a professional water organization like American Water Works Association, California Rural Water Association, the Association of California Water Agencies, Rural Community Assistance Corporation, or any one of a number of other organizations. As soon as you identify a contamination problem, you should contact the Department of Health Services Division of Drinking Water District Office. DHS will help you to identify problems, refer you to third-party assistance, and help you to identify information on financial assistance. They may also suggest that you consult with engineers and/or scientists to identify solutions. When you hire consultants and engineers, remember that you are in charge. Make sure that the engineer looks at options that are appropriate for your water system. Don't jump right to the treatment option. This decision may saddle the system not only with capital cost, but also with ongoing, higher than expected operations and maintenance costs. Be careful to explore approaches thoroughly. One way is to merge your system with another. Even if this means going out of business, better now than bankruptcy later. Another approach is to find a new source at a second location that does not have a water quality problem. In the long run, drilling a new well or finding surface water is probably less expensive than treatment of contaminants at an existing source. Treatment should be the last option you consider. And if you do choose treatment, there are a lot of very important considerations you need to study. Treatment needs to be adequate for the size of the water system. It needs to be an appropriate technology, and it has to be cost effective. It is extremely important to look at the long-term costs of operating and maintaining a treatment plant. What may appear to be the best buy up front may not necessarily be the best long-term solution. You need to look at the cost of the operator. Does the operator have to be trained? Does the operator need a higher grade of certification and a higher salary? Does the operator have to visit the plant more often? You need to look at the cost of chemicals and filtrates. Do they need to be replaced or regenerated? You need to look at the cost of energy. How much more power are you going to need to run the plant? You need to look at increased monitoring costs and laboratory expenses. And you need to look at the cost of waste disposal. It can be very expensive, and you will have to comply with more regulations, especially if the waste is considered hazardous. Of course, the physical size of any proposed treatment unit or plant may be prohibitive. Will the treatment plant fit at the site? Is it compatible with its surroundings? Are there adequate utilities available? Is there room for loading and unloading? Will the neighbors be happy? As part of the treatment option, consider blending as a possibility. You may only need to treat a portion of your water supply so that after blending it back into the original supply, the water is in compliance with MCLs. Blending can save on chemicals, waste disposal, O&M, and capital costs. Whatever your solution for solving the contaminant problem, make sure that it is equitable for the community. Make sure they are involved in any decisions that may affect them. You may have to raise rates, the kind of customer service may change, and even the water may taste different. Arrange for public meetings. After all, the water belongs to them. Finally, the Department of Health Services has to approve any interconnection with another system, any new source, any blending of existing sources, or the addition of treatment. Any change that you make will have to get permit approval from the Department of Health Services. Well, that's it for this program on approaches to compliance with standards. We would like to thank all of our guests for their advice and help in working through this process. We would also like to thank the East Valley Water District, the County of Sacramento, and the Linden County Water District for letting us visit their facilities. At the end of this program is a list of all the segments available in this series. I'm Dave Bender. Thanks for watching.